Third day in chapter 7. Now we're going to make things move a little bit. So we're going to get into this concept that we're going to call a solid of revolution. Solid of revolution. I'll get to what that means. But what we've really got here, if I start with this innocent-looking rectangle and I revolve it around the x-axis, in other words, if we pretend like it's attached to the x-axis right here, and we take it and we kind of revolve it that way, if you follow that curvy arrow that I just made, what are we going to create? Well, we're going to create this this disk, for lack of a better term. This disk that's going to be about, well, it's going to look kind of like a circle right here and a kind of a little circle right there. It's going to have some depth to it, but it's going to take this thing, it's going to take on this, basically this three-dimensional shape. And this three-dimensional shape, and I don't, my apologies for not being a very good artist, but when you've kind of got this x-axis rolling through here, sort of like that, and if you revolve that, you make this, they call it a disk. I prefer to think of it like a quarter or something like that. And if I wanted to find the volume of this disk that I have here, the volume of that disk, well, let's see, that's kind of like the quarter would be like a stack of circles. So I would need to find the area of one circle, pi r squared, and I would need to multiply it by how thick it is. Well, its thickness we're going to call delta x if we go back to our days of Riemann sums. So we're calling that thickness change in x. So I'll have this stack of quarters that's delta x units thick. So I've got a stack of pi r squareds that change in x units thick. So how does that help us? Well, what we're going to do is we're going to take this curve, this f of x that's over here in this second picture, and we're going to revolve that now around the x-axis. We're going to take this thing and we're going to revolve it this way, just like we just did that little tiny rectangle, that representative rectangle that we have. And if you take that and revolve it, what you're going to form, and this is going to be a little bit harder for me to draw, but I'm going to try to do it anyway, you're going to form this thing that's going to be kind of like a, well, let's see, we've kind of got a little area of 3 dimensions to it, and it'll be, if I can draw the mirror image of this thing, there would be it would look something like that. We're going to make this three-dimensional thing that's got this axis running through the middle of it, and it's basically going to look like that. So if we revolve it, we're going to form this three-dimensional figure, and this three-dimensional figure is what we're going to call a solid of revolution. We're going to form it by revolving a curve, and the best example I can give you of this is take a look at your water bottle. Take a look at your Gatorade bottle or whatever sports drink bottle you happen to be looking at. How do they make that? Well, they make this by doing this thing that's called the solid of revolution, and then hollowing it out with plastic, or taking the plastic out of the middle of it, and coming up with what this figure is. So here's what we're basically going to do. We're going to take a whole bunch of these little discs right here, and we're going to put them side by side until we make that solid of revolution. Now, how exactly is that going to happen? Well, what's basically going to happen is this. We're going to take this thing and we're going to break it down, and I'm going to use this picture that I have. I'm going to make it a little bit bigger so it's a little bit easier for me to draw on. We're going to take this picture, and inside here we're going to put a bunch of these rectangles, kind of like what we did with Riemann sums. Because now if I take a bunch of these blue rectangles like I made over here on the left and I revolve them, I'm going to make a figure that's going to look something like this. It's going to look something like my solid of revolution. And it's not going to be perfect, but it's going to give me an approximation. Well, the more accurate I make it will require more rectangles. So what are we going to really do here? We're going to do a little sigma, going back to our old friend sigma. I made 4 rectangles right here. And what would I need? I would need to know each rectangle's individual volume so then I could add each of the 4 together. Well, how did I find the volume of that one? I used this formula right over here. I did pi times my radius, r sub I, my first radius, my second radius, my third radius squared, times that change in x. So that was what I did to put together each of those. Now, we're not going to spend a lot of time with sigma. I know that people are going to start freaking out that we're going back to Riemann sums. We're not. We're going to take this now, and we're going to metamorphosize this thing quickly into, well, what happened before we morphed this thing into an integral, and that integral went from the lower bound a to the upper bound b. The change in x became our dx. The pi is a constant that can be pulled out, and our radius is really the distance. If you look at each of these radii, for example, this one right here, this radius is the distance for however far it is from f of x down to that curve. So my radius, my r sub I, depends on what f of x is. So this radius is about to come my radius, or my f of x, being squared. So this thing that I just made right here, this yellow thing is going to have something to do with what we call the disk method. So backing this out a little bit, what we have that inside that yellow circle is kind of our way that we're going to work our way through these volumes of solids of revolution. So disk method, here's what you've got. So if you are revolving it around a horizontal axis, much like the one that we just drew up there, we're going to take this thing, and this is how you're going to find your volume. So you're going to find the volume by doing pi, because I need it for the area of a circle, integral from a to b of my f of x, because that's going to be my radius, as I pointed out in orange up there, squared with respect to x. So that's if it's horizontal. If it's vertical, on the other hand, now everything in the problem is going to be in terms of y. So if my region, whoops, sorry, let's go C to D instead of C to B so we don't confuse with the same letter. So if my region goes from C to D this time instead of A to B like the last one did, now everything in the problem is going to be in terms of y. So my volume this time still starts with pi, because I got to have it for that ultimate pi r squared that we started with, integrating from C to D, and those have to be y values of that f of y now, my function in terms of y, can't have any x's in it, squared with respect to y. So those are called disk method, and this disk method thing is kind of the most basic of the three you're going to learn. We're going to learn washer method in our next lesson, and then shell method eventually. But that disk method, and I'm going to try to keep it on the screen while we do this problem number one. So this problem number one, we can bust out our calculator and take a look at what the graph of square root of sine of x looks like. And we're going from 0 to pi. So let's use our calculator to help us. I already have this thing ready to go. So there's my square root of sine of x. And I'm going from 0 to pi. So I'm going to change my window really quick. So let's do my window settings, and let's make my x min, whoops, sorry, let's make it be 0. And let's make my x max be pi. And I think that'll work out really well. And hit OK. So there's my function. And now what I'm going to do is I'm going to take that thing, and I'm supposed to revolve it. Let's make sure I get this right. Revolving it from 0 to pi about the x-axis. So I have, if I'm going to draw a picture, I'm going from 0 to pi. There's my function, and I'm supposed to be revolving this thing about the x-axis. And I try to make a little visual for myself. That is not a circle. That is meant to be an arrow that's going around the x-axis. So that's what I'm doing. And I want to find the volume. So to make a visual, if you wanted to think about it that way, this is kind of going to make like a football when I revolve it. And so if that's going to make a football, I'm trying to find the volume of this football. And the way we do that using calculus, this looks like a horizontal axis. So I'm going to use the red up there. So my volume integral from, well, what are my bounds? Looks like my bounds are 0 and pi according to the picture I saw. I'm integrating that thing from 0 to pi. I have a pi outside for a constant. Again, going all the way back to that little tiny circle that we started with up there, that little tiny blue rectangle that we made. That's where the pi came from, of my function, which is the square root of sine of x. And I'm supposed to square that, again, going back to the formula for volume of the disk, pi r squared, with respect to x. So there's your setup. Now you have a calculator available to you. You are certainly welcome to use it, and I would encourage you to use it. What we'll find is this pi ultimately gets multiplied by 2. And you would be surprised the number of people that forget that pi that's out in front of it. So what we have is we have 2 pi cubic units as we're looking for the volume of this thing. And no units aren't going to be that big a deal because units weren't given in the problem. But we are going to make them cubic because we're talking about finding a volume. So kind of heavy duty. Let's go try another one. So second one, volume of the solid formed by revolving the region formed by f of x and g of x about the line y equals 1. So let's do this again. So let's take our calculator. Actually, not even do it with our calculator. I think this is one we can do without. 2 minus x squared is a graph that we can make. 2 minus x squared, we're going to call that top function. So 2 minus x squared looks something like this. And g of x equals 1. So g of x equals 1 is going to roll right through there someplace. And we're supposed to deal with this particular area. That's what we're trying to find. But we're not really doing area. Oh no, I should probably get those areas out of there because we're trying to figure out volume. And if we're trying to figure out volume, then the area really doesn't have anything to do with it. It just gives us a region. So what I ultimately need right here is I need some bounds. So I need to know for my bounds, when is f of x equal to g of x? So set 2 minus x squared equal to 1. And if I do that, so let's see, so I'm going to move the 1 over it. So 1 is equal to x squared, I think, if I play around with the algebra the right way. So I end up with x equals plus and minus 1. So I have bounds. So we're going from -1 to 1. But now here's the thing. We're supposed to revolve this thing around the line y equals 1. Around the line y equals 1. And again, here I am with that visual. I'm revolving around the line y equals 1. Well, where is that? Well, that happens to be my red line. So if that's the case, I'm going to tell you, put in this rectangle. That rectangle is the key to everything that we do. If we go back and look at the problem we just finished, this rectangle right here tells me what my radius is. The length of that rectangle tells me what my radius is. So when I come and I look at this one, the length of that rectangle tells me what my radius is. Well, is it always the same? No, it's changing. If it's toward the y-axis, it's longer. If it's toward the green dots, it's shorter. So when I'm going to try to work my way through here, when I set up my integral, if I revolve it, I'm going to be using disks again because my pink rectangle is attached to the red axis. So when I go to find my volume, I'm going to start with pi. I'm going to do the disk method again, mostly because we don't know anything else. Where are we going from? We know we're going from -1 to 1. And how long is that rectangle? Well, that rectangle depends on the blue function. And how about this? This pink rectangle, the length depends on the difference between the blue, which is f of x, the difference between the blue function and the red function. The length of that rectangle is the blue function minus the red function. Well, the blue function is 2 minus x squared, and the red function is 1. So if you take those and you subtract them, the length of this cute little pink rectangle is going to end up being 1 minus x squared. That 1 minus x squared is going to be my radius, and I'm going to end up squaring because of the formula. We're integrating with respect to x. Take that, figure it out. We end up here, I think, when it's all said and done, with a pi times 16 over 15, if you want to convert it to a fraction. And so we end up with 16 pi over 15 units cubed. Now, before you go and freak out about what happened with this rectangle deal right here, this is the thing that I find the most difficult. Yes, let's put a little star by that because we're going to need to spend some time there. And I'm sure we're going to talk about that when we're in class together. Last one. So find the volume of the solid formed by revolving y equals x squared over y equals 0 to 4. Y equals 0 to 4. Uh-oh. Y equals x squared. Y is going from 0 to 4. Well, I'm going to tell you, if I'm doing y's, if it says y equals 0 to 4, then this problem, as soon as I set it up, I know I'm going to be using dy. So set up your disk method template. Now I just need to find some bounds. What are my bounds? I already know them. They're 0 and 4 because they're y values. But now, if this is y equals x squared, then that also means that this thing is the same as x being equal to plus or minus the root of y. Now with the plus being the right side of it and the minus being the left side of it, so when we revolve this thing, there's going to be some duplication here. And we'll get into some better detail about this, but I'm just going to use the square root of y. I'm going to use the right side, and I'm going to revolve it this time around the y-axis. I'm going this way. So a little bit different axis of revolution this time. And in order to do this, my function, my radius, is going to be from this axis over. That's going to be my function of y. What is my function of y? My function of y is going to be f of y is equal to root y. Whenever you get y alone, you have a function of x. Whenever you get x alone, you have a function of y. Root y, don't forget the pi in front. Now if I take that thing and I punch it in my calculator, I'm going to end up with a pi multiplied by an 8. 8 pi cubic units. So that's called disk method, and it might take us a little while to get used to that, but we're going to keep trying.